So now we have proved the lemma that we wanted to show. Now we are going to use this lemma. So remember that our S matrix element FSI is given by omega of A, say K, of N at plus infinity dot 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 A at K1 at plus infinity A dagger Ka at minus infinity A dagger of Kb at minus infinity acting on omega. Now note that all these operators are time ordered, and therefore we can write the right hand side as the bra omega, a time ordering operator, A of Kn plus infinity dot 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 A of K1 at plus infinity, and then A dagger of Ka at minus infinity, A dagger of Kb at minus infinity, omega. And another thing we can do is we can write each of these operators inside the time ordering to be partnered up. So we can write, say, A of Kn at plus infinity minus A of Kn minus infinity, and then we can write each of these K1 at plus infinity minus A of K1 at minus infinity. For the creation operator, what we can do is we can write A dagger of Ka at minus infinity minus A dagger of Ka at plus infinity, then A dagger at Kb minus infinity minus A dagger Kb at plus infinity, and end of the bracket, and then the ket omega. So see that, we have a lot of extra terms, generated by these guys. But because there's a time ordering, what will happen is that all the creation operators will float to the left, and all the annihilation operators, extra annihilation operators that we introduced, will float to the right. And because the annihilation operator would float to the right, all these extra terms would destroy the vacuum, and all the extra creation operators will destroy this vacuum. And therefore, all these extra terms that we have introduced do not contribute. But now we can use our lemma to each of these factors to rewrite this expression as I times d4 of x1 or xa e to the power minus I ka xa, and then del squared xa plus m squared, and then I times d4 of xb e to the power minus I kb xb del squared with respect to xb plus m squared. And then we can have the factors for the outgoing particles, and that'll be almost the same thing, say x1, but instead of minus here, it'll be plus of I k1 x1, here del squared of x1 squared m squared, and then dot, dot, dot. We have I d for x of n, e to the power I kn xn, del squared xn plus m squared, and the whole thing will be acting on omega, and then the time ordering of phi of xa, phi of xb, phi of x1, dot, 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 phi of xn. And this is the result that we were trying to prove. This is the LSZ theorem. Okay, so what are the interpretation of the LSZ theorem? Let's make some comments on this. So, asymptotically, the wave operators have Fourier transforms of minus k squared plus m squared. And that means that because asymptotically our particles become momentum eigenstate, that means that this goes to 0. So this means that in the endpoint function that the wave operators act on, the particle states or the propagators, which are on shell, that means k squared plus m squared, the denominator of this thing is going to 0. That will cancel with the wave operator. And therefore, so everything else that is in the endpoint function, because it's being multiplied by this guy, will give 0. But this factor and this factor will cancel each other, giving a remainder that is finite. And in this way, what the LSZ theorem is saying is that these operators are projecting out everything from the endpoint function which do not asymptote to the particle states that we are interested in. So that was comment number 1. And comment number 2 is that notice that the in states, the particles in the in states, they come with exponential factors e to the power minus I kx, whereas the particles in the out state, they come with exponential factors of plus I ekx. And this concludes our discussion on the LSZ theorem.